The first experiment in Chem 1211 is titled Atoms, Moles, Nomenclature, and Solubility. And as the name suggests, this lab is kind of a smorgasbord of fundamental topics in general chemistry. So we'll begin by looking at dimensional analysis and reminding ourselves of the SI system of units and how to use things like prefixes and scientific notation appropriately to manage scientific measurements. And then we'll progress to more chemistry-centric topics, talking about things like atoms and isotopes, the mole and Avogadro's number, and progressing to solubility and precipitation reactions. We'll end up using solubility rules to predict the products when two ionic solutions are mixed together. Let's begin with dimensional analysis and units. So I won't remind you of the SI system of units, but this is the system we'll use throughout Chem 1211 to represent scientific measurements. One thing I would like to mention, though, is the use of prefixes. So prefixes are used before a lot of units so that we can keep their actual values manageable and fold scientific notation into a letter with a common meaning among scientists. So for example, the capital M always represents times 10 to the 6th, capital G is always times 10 to the 9th, little c for centi is always 10 to the negative 2, little m for milli, 10 to the negative 3, and the little mu symbol for micro means 10 to the negative 6. So these prefixes are a way for us to compress scientific notation into a commonly understood letter. The basic idea of dimensional analysis is that we can use conversion factors, which are ratios of one unit to another, to convert one unit to a different unit. And the different types of units may be the same phenomenon, or they may be different phenomena entirely, and these usually aren't thought of as conversion factors, but you can think of them that way. For example, molar mass, which is a ratio of grams to moles, can be thought of as a conversion factor between mass and amount of substance. So for example, we could take 5.0 grams, divide by the molar mass, or if you like, multiply by the reciprocal of the molar mass here, and say if it's 5.0 grams per mole, then that's 1.0 moles per 5.0 grams, giving us 1.0 mole of substance. Because dimensional analysis is all about ratios of units and multiplying and dividing scientific measurements, people will often use this railroad track notation, where the numerator is above the horizontal line, the denominator is below it, and the different vertical sort of tie lines delineate each quantity that's being multiplied. As part of this experiment, we'll do an activity involving isotope analysis of a macroscopic sample of pennies. In the experiment, we'll use pennies with different masses, but I want to talk about this in the context of chemistry, and so I'm going to start with an atom. This is a carbon atom that contains 6 protons, shown in blue, 6 electrons, shown in red, and 6 neutrons, shown in black. The 6 protons and 6 neutrons add up to 12 nucleons total, and so this is carbon 12, and we can represent it with the symbol you see here. If we add one more neutron to the nucleus, we've now made the mass number of the nucleus 13, and so this isotope is carbon 13. Both of these atoms are carbon. They both have 6 protons in the nucleus, but they differ in the number of neutrons. That's the definition of isotope. Now I want you to imagine that we had 15 carbon atoms in a hypothetical microscopic beaker, and we were tasked with figuring out the ratio or the number of carbon 12 and carbon 13 atoms. So either the ratio of carbon 12 to carbon 13 or the number of carbon 12 atoms and the number of carbon 13 atoms. How could we go about doing this? Well, massing the sample of atoms, believe it or not, can reveal the isotope ratio within this sample. So if we measure the total mass in total of the sample, and we know, because we know and understand the composition of each type of atom, the individual masses of the carbon 12 and carbon 13 isotopes. If these are known, then we can figure out these unknown numbers of carbon 12 and carbon 13 atoms, what I've labeled as N12 and N13. These are unknown, and we can think of these as isotopic abundances. In the laboratory, you'll use pennies for this. Pennies made before 1982 have a different mass from those made after 1982, and so there's a nice analogy here to isotopes. So how do we go about solving for the number of carbon 12 and number of carbon 13 atoms in this sample? Well, we have 2 unknown variables, so we need 2 equations to solve for these unknown variables. And one thing to notice right off the bat is that the total mass is equal to the mass owing to the carbon 12 atoms plus the mass owing to the carbon-13 atoms. The first term you see here, N12 times M12, that's the mass contributed by the N12 atoms of carbon-12. And the second term is just the mass contributed to the total by the carbon-13 atoms, N13 times M13. The sum of those two terms must add up to the total mass of the sample of carbon. Secondly, we can notice that there are 15 atoms in the sample, so the two numbers of atoms, N12 and N13, must add up to 15. A key thing to recognize here is that we used chemical reasoning to generate these two equations. We had to appreciate that the total mass had to be the sum of the masses of the two types of atoms, and that the total number of atoms had to be the sum of the two different types of atoms. There's chemical reasoning within that line of thought. But once we get the two equations down on paper, it's just a matter of using our epic algebra skills to solve these equations. So it's very straightforward to solve the equations. It's recognizing their importance and writing them down that's really the tricky part. You'll address chemical nomenclature in this experiment in the form of a worksheet to complete. I don't have too much to say about nomenclature in this video except to remark that there is a link in the description that I would recommend checking out. This has huge tables of cations and anions that you'll find in ionic compounds and allows you to practice naming compounds given a formula and providing a formula given a name. Finally, I wanted to talk about solubility and precipitation reactions, and in particular focus on what happens at the molecular level and how we can use the solubility rules as our best friend to predict the results when two ionic solutions are mixed. So let's imagine what happens when we take two aqueous solutions of two different salts. And to keep things simple, I just have the salts with one-to-one stoichiometry here, M sub A, where M is a metal, and X sub A, where X is an anion, in aqueous solution, are combined with MbXb, also in aqueous solution, and we want to understand what happens at the molecular level when these two ionic solutions react. In the laboratory, you'll take one drop of each solution and drop it onto a transparent piece of overhead projector paper and observe what happens. What you'll notice is that in some cases, a solid will form. What's going on at the molecular level when a solid forms in a situation like this? Well, if we blow up this little drop of water, what we'd see at the molecular level are little ions solvated by water molecules. And when a solid forms, two of the ions that were originally not in contact, so either M sub A and X sub B or M sub B and X sub A, get together and are so strongly attracted to one another that they start getting together and forming a solid at the bottom of the drop or at the bottom of the reaction vessel. The other ions not shown here are just left floating in aqueous solution. So we end up with solid in the reaction as well as an aqueous phase containing those remaining ions, which in this case you'll notice are Mb plus and Xa minus, those ions that aren't really strongly attracted to one another and are happy to stay in aqueous solution, do so while the solid that forms because the attraction between Ma plus and Xb minus is really strong enough to promote the formation of a crystalline solid. The products of this reaction are the MaXb solid and the aqueous ions Mb plus and Xa minus. Now, if you think about how MaXa and MbXb, the reactants, are really behaving in aqueous solution before the reaction takes place, you'll notice that really Mb plus hasn't done anything and Xa minus hasn't done anything in the course of this process. These are what we call spectators, because in aqueous solution they just hang around watching Ma plus and Xb minus, the real players in the reaction, get together and form a solid precipitate. So this is what's going on at the molecular level. When the attraction between Ma plus and Xb minus is strong enough, they'll get together, leaving two other ions in aqueous solution, the spectators. It would be convenient if we could predict the results of mixing two ionic solutions, because not all combinations of ionic solutions undergo this process of precipitate formation. That's where the solubility rules come in, and I would strongly encourage you to not memorize the solubility rules. Instead, use that mental space to appreciate how they're useful. Before we get into that, just a brief word about what the solubility rules are and how they're sort of phrased, they all have a form like this. Salts of X minus are insoluble or soluble, and often the rules list exceptions after this decree that salts of whatever are soluble or insoluble. And of course, we can refer to cations as well, and the most famous cation solubility rule is probably the idea that salts of the group 1 cations are almost universally soluble. The power of the solubility rules is that they allow us to identify those insoluble salts that will form when the component ions can find each other in aqueous solutions. So armed with the solubility rules, we can look at the reactants, look at MaXa and MbXb, and imagine switching the pairs, like changing dance partners, to see if that would result in the formation of an insoluble salt. If so, we should expect the formation of a precipitate. If not, we shouldn't.